Good. All right, so here we go. We're talking about the first day of complex numbers, but I'm starting with a lab here. This is the lab that is called either Calculator Polar Graph Lab or Polar Trig Equations Lab, depending on where you look for the title. But if you put in 4 sine of 4 theta on your calculator, and then I suggest you change this thing right in front of the r equals. If you aren't already in polar mode on your calculator, go to make sure you put yourself in polar mode. But I'm going to change this to what I think looks like a pen tip. You can hit enter over and over again, or however you want to, depends on your operating system. Change this to not just be a line, make it the pen tip. Why? Because then when you hit graph, you can see where the little pen tip is going. And do you get it's drawing over the top of itself now? So the second time around, it was drawing right over the top of itself. Why is that important? Because this one then, when I do a window setting of 2 pi or 4 pi or 6 pi or 8 pi or 50 pi, it's not going to look any different, is it? All right. Now, if I do the steps differently, though, it will look different. Do you agree that 0.13 are kind of small little steps to take as you're going from this angle to the next one we're going to graph to the next one we're going to graph? They're very small little steps. Let's take big clunky steps like 3. That's way bigger steps, right? Now, when I hit graph, it looks totally different. I can't even recognize it. All right, let's take a smaller change and see if we can tell like what was going on. Remember it was 0.1 for each step before? Let's make it 0.4. That'll just be 4 times bigger steps. I hit graph. Whoa. You see it's closer to what it was before? All right. Still kind of a cool looking shape. Do you get how you can get cool looking shapes by changing these? I didn't even change what I'm graphing. I'm changing how it's graphing it. Let's, instead of doing 0.4s, let's do 0.2s. That's only double the size steps. And it should be a lot more like it was before. Oh, there we go. See, except it's kind of pointy, and it did make a difference when it went past 2 pi. If you want to see your graph better, if you hit zoom in, sometimes, remember, you have to hit enter twice to make it actually zoom in. You can get a better picture of what's actually happening. See how it is over, it's like not exactly drawing on top of itself now? Okay, moral of the story is, do you get, I haven't even changed the function. All I've changed is my steps. Okay, so what are you going to do? I want to show you one more cool one, and then your job is to just make a cool graph that hopefully nobody's ever seen before. Not new in the entire world. I'm sure some kid in Topeka was playing with the same function you will have been, and they'll get the same graph. But my point is, maybe your friends' graphs and your graphs should all look different. Okay? You should come up with your own unique one. Here's another one that's very popular because it's so simple and so cool. If you go to the next slide of the smartboard, it has it. 0.1 times theta. Just 0.1 times theta. That's it. And then I graph it. And I'm already zoomed in, so it makes it look cooler for me. If yours isn't zoomed in, you might want to zoom in. And mine is going, do you get mine went around more than once? Mine went around twice. Why did it go around twice? Because I had my, yes?
You had your,
what's it called?
The
Theta max. At 4 pi. Good. Yet if I wanted to go around again, I could make it 6 pi. 6 pi is above the caret key. Graph. There went around once, and then twice. And, oh, sorry, I was slow there. Okay. Now, let's change the steps. Go back to window. Change your theta step to, let's make them more clunky. Let's make them like 0.5s. And see if our graph looks different when our steps are bigger. Are you starting to sense a little bit of segments instead of curves? Seeing that? All right, go to window, change it to steps of 2. Isn't that cool? Not even a curve anymore, because there's pretty much straight lines, because there's less total steps graphed. Our steps are bigger. Okay? How about if we make it go to window, maybe I should change it to theta max doesn't have to always be pi's. I could just say the number 200. And then I'm going to zoom out, see what it looks like a little more clearly. Come on. Come on, calculator. There we go. Zoom out. See how there's a spiral built in out of triangles? Good stuff. Okay, so anyway, that's just some playing around for a few minutes. That's what you do. And let's say that you have come up with one, not this one. I did this one. You find a cool one of your own. In fact, you find 3 cool ones. And notice, all I was doing was playing with the steps and playing with the theta max. Now, you don't have to use this 0.1. Maybe you want to use sine of 0.1. Maybe you want to use 0.1 sine. Maybe you want to use sine, cosine, tangent of 0.1 theta. You play with it, find something that's cool, and then you're going to take a screenshot of it and put it right here. See? Right over the top of this, you're going to put a picture on there. You're going to have this in Notability, right? And you know how to import pictures in Notability? So you take your calculator, have it on your calculator, and then you use your iPad, and you just take a picture of it, and then you maybe zoom in so it's just the graph, because that's all I care about is the graph. And you put it on here, and you have to tell me what it was, of course, so that it can be replicated. We don't want your creation to be lost forever when you forget. I don't know what it was, but it was really cool. Write it down here, 0.1 theta, but I used a theta max of this, and I used a point. Do you have to use 0.1 theta? No. If you want to base it on a spiral, that's a pretty good one, but there's others. And then you just have to answer 3 little things about, you're interrupting now. You just have to answer 3 little questions about your graphs. No, sentence 1, and I'm okay with abbreviations on this. What are the coefficients? Okay. Number 2, describe why you stopped at the theta max that you did. In other words, it would only look like this if I did a theta max of 2, whatever. Sentence 3, describe why you chose the theta step. Okay, so you take your graphs and you're telling us basically why you used that theta max and why you used that theta step, and basically what was different about the graph when it only had more steps or less steps, or what was different about it when it had a bigger theta max. All right, so you find me 3 graphs like this. It's still worth the same points as a lab, but you don't have to use the normal lab format where you have to have conclusions and procedures and calculations and all that stuff. Just take 3 good screenshots, tell me what they were, and answer a couple questions about them. Right, that's the lab. It's not due till next week. Maybe we'll have lab correcting day next week if it ever eases up, but it's been really intense lately. But again, you guys have been rising to the occasion, so it's really good. I'm happy that even though we've been moving really fast, you've been holding on really good. The test scores were very good in your hours, so nice job. Okay, I now need to get to complex numbers, and I know some of you are going to be playing with graphs the whole hour, so take your calculators and stuff them back in your backpack, please. If you borrowed it from me, come and make the trade back again. Ah, gotcha. Yes, you are supposed to leave me collateral for future reference. Right now we're recording, so how about you just keep on. All right, so your job on today is to notice a couple things about complex numbers. Number 1 thing about complex numbers is that you're not allowed to have square roots in a denominator, and I, which is part of any complex number, remember I stands for the variable we use for the square root of -1. Does that ring a bell? That I is a square root, isn't it? All right, so you can't have square roots or i's, which are square roots of negatives, in the denominator of a fraction. There's your big thing for today. Okay, I'm going to show you a lot about that, but Let's go back to what is a square root. What's the square root of 25? It's 5. Good, because 5 times 5 makes 25. So what's the square root of negative 25? Don't just say 5i. What is the square root of negative 25 when you break it into two things? It would be the square root of what and the square root of what? Square root of 25 and square root of negative 1. Do you get how that times that makes the square root of negative 25? Okay, and then this works out to what? 5, and that works out to what? That's why it's 5i. Okay. So, what's the square root of negative 4? 2i. Because why? Because it's two square roots, really. What are the two square roots? 4 and negative 1. And then this comes to 2, and this comes to square root of negative 1 is I. Okay. Good. Next thing. If you have 1 over x, it's fine as long as x isn't what? 0. Okay. But is this okay? No. So you could simplify, or you could fix this by just simply multiplying by something that would make the square root not be there. What can I multiply by that would make the square root not be there? Square root of x. If I do the square root of x and the square root of x, like this, I'm really multiplying by 1, so it's totally legal. And this part becomes what? Just x. Do you get square root of negative 3 and the square root of negative 3 makes negative 3? It's like a definition of square roots. How about this? Square root of 2.93 times the square root of 2.93 is equal to what? 2.93. All right. How about this one? Square root of negative 1 times the square root of negative 1 is equal to what? Negative 1, which is the same as I squared. Do you get how this was I and this was I? So it's I squared. That's why I squared is negative 1. How many of you remembered that coming into today? That's the biggest thing for the ACT test, is they throw in I squareds every now and then to see if you know, oh, I should change that to negative 1. Okay? So if you had 3 plus I and 3 plus 2i, and you multiplied them out, do you get at some point you'd have an I squared in there? After you do the first, outside, inside, and last, you'd have an I squared, right? Why is that good? Because you can replace it with negative 1. Okay, so let's actually do this one. Everybody multiply this one out. It's got an answer that does have a plain I in it, but it also has an answer part that has an I squared in it. Nine is my first. My outsides makes 6i. My insides makes 3i. And my lasts makes, there it is, waiting for the payoff. It finally came. We got an I squared. Now I can actually combine these two because they are like terms. So 9 plus 9i plus 2 times negative 1. That's what the ICT will be looking to see if you know. And then 2 times negative 1 makes negative 2, plus the 9 makes 7. 7 plus 9i. Now let me ask you, wouldn't that be the exact same thing as 9i plus 7? Pretty much, but one of them is the preferred way to write complex numbers. Do you think it's A or do you think it's B? All right, it is A. The imaginary part should come last. Do you get how this is just a real, plain, normal 7? And this part is imaginary. It's kind of made up, as in we made up a little thing to make negative square roots work. And okay, so this is called a complex number because it's got both real and not real parts. Do you get how you might have a complex personality because in some ways you're really deep because you want to talk about, you know, whatever. And then in some ways you're kind of shallow and abrupt with people. You're complex. Imaginary numbers don't really want to be called imaginary. They prefer to be called complex. All right, so anyway, you got your real part, you got your imaginary part. but always put the imaginary part last, you got a complex number. The title of this whole unit is called complex numbers. There you go. They have real parts to them. They have imaginary parts to them. All right, so what is a typical problem for today? It'll be typically like this. 4 plus I divided by 2 minus I. Why can't I just leave that alone? Because it's got an I in it, which is really a square root. Is it okay to have I's? Yes, but not where? On the bottom. Therefore, how do I get the I out of there? Well, does anybody remember a technique called conjugates? All right, so what's the conjugate for 2 minus I? 2 plus I. That's all there is to it. Now, what's the magic here? Because when you FOIL it out, watch what happens. First make 4, pretty innocuous. The outside and the inside is where the real magic happens. What happens with the outside and the inside? They cancel. So it's going to be simpler than just any normal FOIL problem. And then how about the lasts here? What's I and I make when you multiply them? It's negative I squared. Good. And then the I squared itself is equal to negative 1, and that makes it 4 plus negative 1. Which means what? 4 plus 1, which makes what? The denominator is just 5 now. Do you get how that's better than it was before? All right. But by multiplying on the bottom by 2 plus I, to keep it fair, I got to multiply the top by 2 plus I. Would everybody please multiply the top? And warning, the top will not be nice and clean and have no middle term. It'll have a middle term, and that's okay. As long as the denominator doesn't have i's or other square roots in it. The answer is something over 5. Figure out the top for me. I'll pause for a second while you do that. So, did you get first 4 times 2 is 8. Outside 4i, inside 2i makes 6i, and last makes I squared. Ooh, wait a minute. Maybe I should make that a negative 1. Put it with the 8. Now it's 7 plus 6i. Raise your hand if you had 7 plus 6i. All right, good. What was any better about the final answer than the first answer? Doesn't have a square root in the denominator. Okay, good. So, a couple of little things for terminology. Let's say I had 5 plus 2i. What's its conjugate then? 5 minus 2i. If this was called x, then there's a terminology for saying conjugate that's a lot simpler than writing out conjugate of x. It's that. Put a line over it, it means conjugate of. So if they said, this is x, and they wanted to know what's x times x line, what are they really saying? Take x and multiply it by its conjugate. So what would the answer actually be? Everybody do that one. Take x and then multiply it by its conjugate, and then tell me what you get. It's kind of cool when you get into these complex notations that make it look like you're really smart, but it's really not that complicated. You are smart, but it makes you look even smarter than you actually are. Okay, so you have 5 plus 2i, and you got 5 minus 2i. Notice I only changed the sign in between the two. That's especially important if it had been negative 5. If it had been negative 5, it would still be negative 5 plus 2i, and it'd still be negative 5 minus 2i. The only difference would be the middle sign. All right, so back to what we actually had, which was this. And you should have said that x times x conjugate is 25. Outside, inside cancel. That's cool about conjugates. Last is negative 4i squared. I would write it out that way to start with. And then you can replace this with negative 1. And then that becomes positive 4 with 25 makes 29. Raise your hand if you had 29 for your answer. Okay, good. All right. So I think you've learned as much as you need to know to be able to handle today's homework. So I'm going to pause for a second while we get there. Okay, so let's work through this first one together. This is assignment number, or day number 1, and it's got a bunch of parts to the same question. It says z is this and w is that. So what's z plus w? Well, just put -5 plus 1 plus 4 plus 2i. Now, if it had been in minus, if I was subtracting these two, do you get I'd be really careful with like putting this in parentheses so I distribute the minus sign to both of them, but it's not a minus, so I won't worry about that. Pause for a second. So, on this one, what can go together? Well, the 4 can go with the -5 and make -1. The I can go with the 2i and make 3i. And that's it. Notice I'm putting the imaginary part last. That makes a complex number answer. That's it for part A. Part B is 1 over z. It seems like it should be as simple as just put 1 over z, which is 1 over -5 plus 1. Or, sorry, I. But you can't leave it that way, because why? It's got a square root, the I, in the denominator. So you got to fix it. So you got to know how to fix that by multiplying by its conjugate on the top and the bottom. I'll let you finish that. This just is asking for what is the conjugate of z. That's all it's asking for. This is that simple. So here's z, and its conjugate is the exact same thing, except in the middle, make it minus. This is asking you to multiply z and w. This one's asking you to divide them. Anytime you divide, you're probably going to have a square root in the bottom, and you got to fix it. And this is asking you to multiply z times its conjugate. I think you get how to do those things. It shouldn't be too tough. Now, there's 2 pages like this. I helped you with this one, and there's this one. I want you to do both of those pages. These aren't that bad. Yes, this has a square root of 3 in it, but it's not that hard. You can handle it. You multiply the square root of 3 times the square root of 3. Remember what happens. When you do have this situation, what would that answer be? Square root of 9, which is 3. Whatever was underneath it comes out. Okay. So that should be pretty straightforward for honors pre-calc class. This actually is embarrassingly easy. So this is as simple as it seems. What's the answer for number 11? If you know it, say it. 7i, done. They're that simple. Okay? And the ones at the end, says be careful with these. There might be a reason for that, because a lot of people make dumb mistakes by just doing it really quick and they think they got it and they don't. All right? And these two also just have a little twist to them, so be a little careful. This last part is just, I need to remind you, you did this in honors higher algebra. I know you did. I teach that class. I know you did it at one point, but you probably forgot. I to the 5th can be made up of a whole bunch of I squareds. I squared, and an I to the 1st, yes. And what's that equal to? And what's that equal to? -1 times -1 times I. And so what's the answer? 1i, which is the same thing as I. Okay? So I encourage you to take all of these. I'm going to actually let you skip the last 3 because this kind of gets redundant. And make them into I squared to the something. Maybe you could say I squared times I squared times I squared, or I squared to the 5th, or whatever it is. Make them into I squareds. And sometimes you have to have a leftover I. And like in this first one, the answer will have an I in it. All right? So make it up into a multiply problem with a bunch of I squareds. Or a power problem with a bunch of I squareds. All right. Good enough. That's your homework for today. I think that's doable. All right. That's all I have for the lesson for today.